Let's talk about what happens when you're given a system of differential equations, and now you're also given an initial value condition, which allows you to solve for the coefficients of the differential equation or of the system, right? So when you have a system, you're left with like c1 times a vector plus c2 times a vector, and if it's a 3 by 3 system, you also have a c3 times a vector, and once you're given the initial value condition, you can actually find C1, C2, C3. So how do we do that? Well, consider then this problem. So we're trying to find, wrong color, trying to find x prime is equal to ax. And you're given that x naught is equal to something, right? Equal to some vector. And in our case, then, we have a is equal to, let's say, I'll make this short and sweet. A is equal to -2, -1, 1, 4. And let's say x of 0 is equal to 0, -1. All right. So how do we find find the solution to the system, right? The answer is this. So x naught some vector. The answer is we leverage this equation. E to the at is equal to x of t x naught inverse. All right, and this may make absolutely no sense right now when you're looking at this, which is fine because we want to find x of t, right? So eventually we have to multiply both sides by x naught, and so you actually see that e to the at x naught is actually equal to x of t. Okay, and okay, well, technically speaking, I think it's like written in their book as x inverse at 0. Okay, it's fine. We'll live with it. So what does that mean? So that means I need to find e to the at, right? So find e to the at, which is we've been doing for ages. Okay. And then what is this? This becomes actually 2 plus lambda times 4 plus lambda plus 1, which is lambda squared plus 6 lambda plus 9. And the reason why I knew that was because if you factor out a negative sign and you factor out a negative sign in here, so you get -1 times -1, which is +1, and then you factor out a negative, so you got 2 plus lambda and 4 plus lambda. And then, okay, so this means that lambda equals -3 with multiplicity 2. Okay. And now, so we look at lambda equals -3, and that gets me the following. I get 1, -1, and then 1, -1. Okay. And of course, we run into problems here because this is defective. So, right, this multiplicity is equal to 2, and the nullity is equal to 1. Okay, and that's because if these two rows are the same, this row and this row are the same, and so you can only get rid of one of them, and so the rank is 1, which means their nullity is 1. And then Sj, right, so now we want to find S and J because that's the easy way to find this. So J will have to be, it looks like -3, -3, 1, because there's only one block. That's what the nullity tells me. And then S will be the following. So this guy squared is going to be, so this is a plus 3i, and a plus 3i squared is going to be 0. I have no doubts about this. So then I'm going to let VG be 1, 0, and then a plus 3i VG ends up being 1, 1. Okay, and so S is now 1, 1, 1, 0. And the inverse of 1, 1, 1, 0 is S inverse. I'm going to use the determinant trick. So the determinant's -1. And then so you flip these guys, and then these guys are negative. And then since the determinant is -1, you do 1 divided by -1, which is still -1. And so when that multiplies through, you get positive 1, and negative 1. Okay, and 1, 0, 0, 1. Yes, that works perfectly. And now e to the at is equal to s e to the jt, which is e to the negative 3t, e to the negative 3t, and then t e to the negative 3t. Okay, this you need to know how to do this really quickly. This is e to the jt right here, and then s inverse. Remember, go watch the videos on Joint Canonical Form. If you don't remember why, I can just do this quickly, or I'll explain in class why you can do this exponential really quickly. I'm pretty sure I did it in a video. Okay, and now what is this? This is e to the negative 3t, 1 plus t e to the negative 3t, e to the negative 3t, t e to the negative 3t, and now 0, 1, 1, negative 1. This is 1 plus t e to the negative 3t. Okay, this minus that. So now you get negative t e to the negative 3t. That's a funky looking 3. And then t e to the negative 3t. And then 1 plus t e to the negative 3t. Okay. And now, oh, is that 1 plus or 1 minus? That's 1 minus. All right. And so remember this right here, e to the at times x naught is equal to x of t. And so this is e to the at, right? And this is e to the at. And so e to the at, x naught, x at 0 is equal to x of t. So now we just take e to the at, which is 1 plus t e to the negative. I'm going to factor out an e to the negative 3t. Okay, so now this is just 1 plus t, t, negative t, 1 minus t. And then x naught, if we recall, was 0, negative 1. Okay. And now you just multiply. Well, 0, negative 1 just takes the last column and puts a negative sign in front of it. So now this becomes e to the negative 3t times positive t, and then t minus 1. Okay, and this is then your initial value condition for your system of equations up here. Right, so right here, yeah, this is the problem. So here's your problem, here's your matrix, and I get that this is your solution is equal to x of t. And so you inherently just solve for all of the coefficients in your system, and this is a lot faster than, well, it might be faster. You can solve each value one by one, so you can actually create your generalized, right? You can create you can follow the method of the cycle to find your two linearly independent solutions from like a previous video. Like I think it's like the video immediately previous this, and then from there you can for each equation solve for the unknown coefficients. I think this is the better way. I think this is the better way. This is the only way I'm going to teach, or I'm going to teach the recitations. It leverages the use of the exponential very cleverly, and I think it's the better way because it's the better way. So all right, that's it for initial value conditions, and then I have one more thing about systems of differential equations, and then we'll move on to phase portraits.